at one point of time during the last lecture, you probably asked yourself, why are we talking about dielectric double layers and how are they relevant in microfluidics? And this is the question we are going to answer in this video. So let's have a closer look at the situation presented on the right-hand side. Well, there's a liquid colored in blue. There are ions within this liquid. There are two electrodes on the left and the right-hand side, which are where a voltage is applied. And there is a charged wall due to, for example, a simple surface treatment. And by now you should understand what happens in this situation. The negatively charged ions will be attracted by the wall, and there will be a dielectric double layer at the wall. If we now consider the electrodes on both sides and the charge density within our liquid, we will see that there is an imbalance. The area close to the wall will be locally negative charged, whereas the bulk solution will have a neutral charge. And this local negative charge is attracted by our positively charged electrode. This results then in a force directing into the direction of the positively charged electrode. By now you should have an understanding of fluidics and the forces that are involved. So if the outer layer is moving slowly into the direction of the positive electrode, there will be friction between the different layers, and the friction will result in the next layer moving into the same direction. And this is how this local charge and due to the dielectrical double layer results in a flow profile in direction of the electrodes. How can we describe the velocity profile originating from the dielectrical double layer? To do so, we come back to very familiar equations, but let's start first with the assumptions that we have to do to continue with the calculation. So we assume that it is a flow along an infinite plate and that there's liquid in direction perpendicular to this plate. We assume that the dimension in x direction is a lot larger than the dBi length. We assume a steady state, so there are no temporal changes. We say that there's no pressure gradient, so there's the only driving force will be the electrostatic, the electrokinetic effects. We neglect gravity, and we assume that there's no turbulence, so that we are only looking at low Reynolds numbers. And to determine the velocity, you can start with the now well-known Navier-Stokes equations, including on the right-hand side the electric forces. So we know that the velocity in y direction at the position of x0, so at the position of the wall, is going to be 0. And we know as well that if we are far away from the wall, the velocity in direction of y will not change. So this means that at one moment in time, the velocity will get constant if we are far away from the wall. Thanks to the assumptions that we made, we can simplify our Navier-Stokes equation. So there are no volume forces. There is no pressure gradient, and we only consider a flow at low Reynolds numbers without any temporal change. And this leaves us with two terms. One is the one is based on the electric forces, and one is based on the viscous forces. If we get rid of all the unnecessary terms, we consequently end up with this equation. And I want to simplify it further because we are only interested in the velocity in y direction. And that's why we only use this direction for the next calculation steps. So once again, we make use of the Poisson equation to solve the upper equation here. And we then enter the charge density into our equation here. And that's why we end up with this simplified Navier-Stokes equation, where we have the electrostatic field in y direction, as well as the potential, the electrostatic potential. So now we can make use of the things we learned in the second video, because we know the potential, the electric potential along the x-axis, because we know this is the dielectrical double layer. And if you remember it, you know that we assumed, because of the diffusion effects, there is an exponential, that the electric potential can be described by an exponential function times the zeta potential. If we introduce this equation now into our simplified Navier-Stokes equation, we get this equation with a lot of constants and material parameters. But nevertheless, the integration of this in x direction is quite straightforward. So if we want to find out our velocity in y direction, we simply have to integrate it twice with respect to our parameter x. And as it is an exponential function, it doesn't really change, but we get two additional constants due to the 2 times integration. Here, we then have to remember our boundary conditions. So we said that the velocity in y direction, so in direction of the electrodes, equals to 0 at the wall. If we enter x equal to 0, we will end up with a constant C2, which is equal to this term. So the exponential function equals to 1, and then we only have this term left. And if we use the second boundary conditions, so that there is no change in velocity at a far distance to the wall, we will find out that the constant 1 equals to 0. So we derive it once. This C2 will be 0, and there's only C1 plus this term equals to 0, and the exponential function of minus infinity equals to 0. So the result will be C1 equals to 0. And this means that we end up with a velocity in y direction equal to this equation. So once again, if you are close to the wall, so if x is close to 0, there will be 1 minus 1, which equals to 0. So the velocity gets lower and lower the closer you are to the wall. If you, on the other side, go further away from the wall, the velocity will get closer. So this exponential term will get closer to 0. And we have a velocity of this term here. In between, so it will get constant. The changes will get lower and lower. In between, we have an exponential development of the flow profile. So here you can see another form of the velocity in y direction. We introduced the electric potential as parameter instead of x. And if so we now know if we are far away from our wall, there will be no influence of the dielectrical layer left. And this means that the potential will be 0. And that's how you end up with this velocity far away from the wall. In general, this equation can be used to determine the zeta potential of a functionalized wall by measuring the velocity of your fluid in direction of the electrodes. Very important at this point of time is to understand that this change in velocity happens at a very tiny dimension, usually in the range of the Debye length. And this means that if you have a look on the macro scale of your channel, for instance, the flow velocity will appear to be a straight line, what we've seen at the start of the first video. Well, obviously, not only walls can have a surface charge, but also particles that are in total neutral can have a charge at the surface. And these particles can be considered in a similar way that we considered our walls in video 2 and in this video. And this basically means that you have similar effects around the particles. So you have a dielectrical double layer. You have ions that will always remain around the particles, and ions that will be sheared away with the volume flow that flows around the particle. And if you use the equations that we derived, you can describe and determine an ionic mobility of charged particles, similarly to the ionic mobility that we derived for particles within the electrophoretic chapter.